Within this video discussing ideas from Chapter 4, we're going to be looking at the final section. We'll be considering solution stoichiometry and titrations as an example of solution stoichiometry. In the overview for the chapter, one finds that titrations are one of the most difficult sets of learning objectives for students when they're working on Chapter 4. Why are titrations so difficult? This is something I've studied. I found that titration questions are often scenarios and story problems that combine numbers with chemical information. Think back to when you experienced story problems in the 3rd grade. They were a lot more difficult than if you were just given numbers and it was clear how to manipulate them. Students often struggle to connect information in a story problem with what they already know. It seems quite different when there's extraneous information, or what the student perceives as extraneous. They're not sure which values they're supposed to use and how they're supposed to use them. Oftentimes, students don't organize the information. For example, many times they don't write a balanced equation. Students frequently begin simply using the numbers that are given in the question. They don't pause and first ask, well, what is the chemical context? This idea of writing a balanced equation, my number one suggestion for titration problems, please write a balanced equation. Right there, that will improve your chances for success. We've seen before that we can use solution information to get the number of moles. Here's a neutralization reaction involving hydrochloric acid and sodium hydroxide. The sodium hydroxide is aqueous, so we have a concentration given for it, a certain molarity. Molarity, you recall, is moles per liter. A really useful skill for us is to be able to combine solution information to get number of moles. Concentration in molarity times volume in liters gets the number of moles. So in this question, we needed 0.50 moles of sodium hydroxide. We had information for its concentration, and we solved for the missing variable, the volume. Here's the same reaction, but now I changed the wording so it's a titration. In a titration, 35.52 mils of 0.105 molar sodium hydroxide is needed to neutralize a solution of hydrochloric acid. How many moles of HCl were present? Same kind of problem. In this balanced equation, the titrant reacts with the analyte 1-to-1. The titrant is the solution that we're adding. I would say that we're adding the sodium hydroxide. We have all the information in terms of the volume and the concentration. That was being added to a solution of hydrochloric acid. That's what we were seeking to analyze. That was the analyte. In this balanced equation, they react 1-to-1. Those are what the coefficients are. I'm using the term in this balanced equation because that's not always the case, right? Until we balance it, we don't know what the coefficients are. Pause for a second. How many moles of sodium hydroxide were used in the reaction, and how many moles of HCl were initially present? Work through those calculations, share your answers. In my solution, I'm going to combine the solution information, molarity times volume, to get to number of moles. This would be my calculation to say how many moles of sodium hydroxide were involved in the reaction. And because in the balanced equation they react 1-to-1, that's how many moles of the hydrochloric acid were initially present. How about this one? In the titration, 15.52 mils of sodium hydroxide is needed to neutralize 20.00 mils of 0.225 molar nitric acid. What is the concentration of the base? Analyze this question. How is it similar to the previous question? How is it different? How would your plan be similar or different? I'm not necessarily asking you to go through and solve it, but within your analysis, what similarities do you find and what differences? Share those responses. Here's how the textbook describes titrations. It begins by noting that we will have solutions reacting with each other, and we might have different variables within that. We might be interested in the solute concentration in the solution that we're adding. We might be interested in a volume. There's different variables, but what's common is we're going to have one solution react with another. The equivalence point, that's when stoichiometrically equivalent quantities are brought together. That just means based on the coefficients in the balanced equation. The balanced equation is telling us how many moles react with moles using the coefficients. That's what it means to reach the equivalence point. When moles of one reactant matches moles of the other based on the coefficients in the balanced chemical equation. Procedurally, oftentimes we will add an indicator or something that will tell us when we've reached the equivalence point. And to transfer the solutions, a burette is frequently used because that will allow us to accurately determine the volume that we added. Here's a typical setup. So they are transferring with a pipette a known amount of acid. An indicator is added. They set it up so they have a burette above it. Acid was, in this case, in the flask, and sodium hydroxide was added to the burette. In this example, that's a standard solution of sodium hydroxide. Standard meaning the concentration has been determined. So the variable in this case would be, tell me about the acid. It's important within a titration question to ask, what is the variable we're seeking to find? In this case, we're interested in information about the acid, which was the unknown, and we're using a standard solution, which was the base, to find that. When we reach the equivalence point, the change of color is indicated. The outline for how to solve problems involving titrations, this is how the book presents it. Let's take this now and connect it to what we already know about stoichiometry. Right in the center there, it's pointing out you need a balanced equation because we need to use the coefficients of the balanced equation to figure out how moles react with moles. Crucial first step. Start with a balanced equation, and we need the coefficients to see how moles will react with moles. Next part is we're using information about the solutions. Before, when we did stoichiometry with solids, we would convert from grams to moles by using the periodic table, or moles to grams by using the periodic table to look up a molar mass. Only difference now is when we're getting 2 moles or out from moles, it's involving the solution information, the volume and the concentration. If you're proficient at using volume and concentration to get to moles, then this is really just another version of a stoichiometry problem that you already know how to do. Here's an example of a titration question. As I read this, this is a stoichiometry problem, so we need a balanced equation to start. We also need to convert to moles. Read the question, see if you can write a balanced equation, and do you have any questions initially when you read this? Are you able to get started on it? What are your concerns? Share your ideas. Let me work through this one and show you how it's connected to things that we've already been working on in this class. So that's my balanced equation of sulfuric acid reacting with sodium hydroxide. Absolutely start by writing a balanced equation. The portion of the question that's relevant to reach our answer, what is the concentration of sodium hydroxide, I list above it. I'm going to show how this can fit together using a BCA table, because that's a framework that we've already looked at for solving stoichiometry problems. And in fact, when we're using a BCA table for a titration, we really only need to be looking at the reactants portion. So based on the information, what can we first add to the table? Is it going to be moles of acid or moles of base? I think it's going to be moles of acid. We have information, solution information, which is concentration and volume for the sulfuric acid. We'll combine those to figure out how many moles of sulfuric acid we have. I'm going to put that in the table. I can think of it as if that's the amount that I started with and I used it all up in order to reach the equivalence point. Now I'm going to look at the coefficients. Using the coefficients in the balanced equation, for every 1 sulfuric acid, it takes 2 sodium hydroxides. So I've just scaled up the number of moles that I'll need for the sodium hydroxide. Same thing that I would have been doing back in chapter 3. And then finally, let's use the concentration information to connect that to number of moles. Concentration in moles per liter times the volume in liter equals number of moles. What's my variable in this case? I don't know the concentration, but I know the volume in liters, and I know the number of moles. That was in my BCA table. The only variable I have left was the concentration, and that's the concentration of the sodium hydroxide. What questions do you have for the information on this particular slide? What I'm trying to do is show how a titration question is really solution stoichiometry, and the same skills that we have for stoichiometry, like a BCA table, are applicable. To finish with, let me show a computer simulation that can generate some data for us. I want you to use the data within the simulation to calculate and report the concentration of the unknown solution. I'm going to have a titration of a strong acid with a strong base and put the base in the burette. Different strong acids to choose from, different strong bases. So I'm using HClO4 as the acid, strontium hydroxide as the base. I added some indicator, and now I'm going to add the titrant, the strontium hydroxide. This is the total amount I've added. 7 mils, 8 mils. Notice how the solution's getting a faint pink color. When it turns all the way pink, I've reached the equivalence point, and it took 10 mils for that to happen. At the bottom, this is the information describing the acid. Give it a try. See if you can use the information to calculate the concentration of the strontium hydroxide.